Hello, I'm Jonathan Heathcote from BBC Research and Development, and today I'm going to tell you how to avoid your video codec producing artifacts like these. All of these artifacts are the result of integer overflows occurring inside a video codec, and it turns out it can be surprisingly difficult to work out how big the integers need to be in your codec to avoid this problem. And, as we'll see later, it can be very easy to convince yourself you've used integers large enough when in fact you haven't. And of course, using integers too large for the job can result in problems for cost-sensitive implementations. In this paper, we introduce a new heuristic for producing test patterns that you can feed into video codecs to work out, first of all, how many bits you're actually going to need to avoid integer overflows occurring in practice, and also to verify existing video codecs use enough bits to avoid these problems as well. When a video encoder is fed a video signal, that signal tends to come in at a nice well-defined range, for example 8 or 10-bit video. As those signals pass through a video encoder, that signal range can begin to change as all of the various processing steps occur. For example, it can grow to be bigger and smaller at various points in the processing chain, depending on what operations your codec is performing. Once your signal has been encoded, the reverse process happens inside your decoder, and eventually those signals end up back in a range very similar to the one you started with. Now I say very similar because of course in lossy codecs it's quite typical for there to be small over and undershoots in your final output picture, which is why most video codecs include a clipping stage as the final step in their processing. But today we're going to kind of ignore that. We're going to focus on what happens inside the codec, because it's here that if you don't use integers big enough for the arithmetic you're carrying out and for the values that you're passing through, you can end up with those unfortunate picture corruptions that can be really easy to spot. Now, perhaps the simplest way to work out how many bits your codec's integers need to have is to feed your codec a series of images and measure how large the signals are as they pass through your system. And as you do this with a large number of images, what you start to see is that each image produces very different ranges of signals. As you can see here, the range of signals can vary by 2 or 3 bits depending on the picture. And it's this variability that makes this method particularly dangerous, because you can very easily end up in situations where your codec has enough bits in all of its integers to avoid any overflows when you're processing all of your test images, but as soon as you send this out into the real world, you might encounter pictures that occasionally just top a little bit over those ranges, and at that point you end up with a picture corruption. Now, just to drive this point home, I'm talking to you right now via a video codec in which I've reduced the size of all of the integers, and so far everything kind of looks fine, but if we change camera angles just slightly, and oh dear, we have quite a lot of picture corruptions, even though this is superficially quite a similar scene. And so clearly this isn't a good way to work out how many bits we're going to need. So what do people do in reality? Well, one of the most robust ways you can work out how many bits you're going to need is by mathematically analysing the signal processing that goes on inside your codec. And at first sight this might seem like a really good approach because, after all, most of the video processing steps that happen inside your codec tend to be linear in nature, and of course linear systems are incredibly easy to analyse mathematically. Unfortunately, there's a catch, and that is that lossy video codecs typically include a quantization stage, and this quantization stage is very much a non-linear process stuck in the middle of what is otherwise a fairly friendly linear system. Now, as a result of this, it means that we're not actually going to be able to exactly compute mathematically the number of bits our codec needs, or indeed what a worst-case signal might look like for our video encoder or decoder. But fortunately, there are methods you can use to compute upper bounds on how big those signals can become inside your codecs. Now, these theoretical upper bounds immediately highlight the fact that our original set of test images wasn't producing signal ranges as high as it's possible to get, and that we were very likely to end up underestimating the number of bits our integers need to be by perhaps 1 or 2 bits in places, and perhaps even more later on. However, using these theoretically computed upper bounds does have a critical drawback, and that is that these upper bounds can include overestimates of the number of bits you need. And here you can see we have these suspiciously tall peaks that maybe indicate that these upper bounds are perhaps several bits larger than the actual worst-case signal ranges might really be. And it's this that means that in practice you probably can't afford to use this kind of technique to work out the number of bits you need in your system, because it means you might end up having to use much bigger integers than you really needed, wasting hardware, wasting power and wasting performance. Working out exactly how many bits your integers require inside your codec is not the only way to avoid integer overflows. Another method, which is popular amongst many mainstream codecs, is to use either saturating arithmetic or adding extra clipping stages at various points inside your signal chain to keep levels within a well-defined range as they pass through the system. Now, this avoids the problem of integer overflows entirely, but this is a compromise. Adding clipping stages or using saturating arithmetic can reduce the quality of the pictures slightly as they pass through your system, and so essentially we're having to trade quality for avoiding the problem. Unfortunately, none of these approaches are ideal. If we use a series of test images, we might underestimate the number of bits we need, and therefore encounter integer overflows out in the wild. If we use our theoretical upper bounds, what we might find is that we've built more hardware than we needed, therefore costing us extra money and performance. Alternatively, we can throw quality away to avoid the problem entirely, but obviously this isn't something we necessarily want to do if we can avoid it. And this is where our work comes in. We've designed a heuristic for producing test patterns that you can feed to a video codec and which deliberately produce extremely large signals inside your codec as the pictures are processed. Now, using these pictures, you can produce a fairly robust estimate of how many bits your codec is actually going to need in its integers to avoid overflows. And what's more, you can use those test pictures against real hardware and real software to verify that you have in fact used enough bits in reality. This work originally span out of a project to produce conformance tests for a video codec called SMPTE 2042-1 or VC2. VC2 is a simple intra-frame only codec, but despite this still follows the same general principles as any other video or image codec, and this makes it an ideal model for this work. In a VC2 encoder, pictures are first transformed into a domain that is more convenient for compression, and in the case of VC2 we use the wavelet transform to do this. Now, these transform values are eventually fed into an entropy coder, which takes the numerical transform values and turns them into a much more efficient binary representation. Now, unfortunately, entropy coding alone is not often enough to produce the bitrate that we actually need for our applications, and so an additional quantization step is inserted into the middle of this process, and this quantization step coarsens the level of detail in our transform domain representation, allowing us to fit within our desired bitrate target. A VC2 decoder, of course, just follows the reverse process. It uses an entropy decoder to get back the transform values, dequantizes them, and then feeds them through an inverse transform to get a natural image back at the end. Now, for the purposes of studying integer sizes within video codecs, we can ignore the entropy coding stage, because this is essentially a transparent step in our coding process, and it's one where it's possible to work out exactly how many bits you're going to need without any trouble. So, how do we produce some test patterns that produce extreme signals inside our codec? Well, let's start by looking inside our encoder. And we'll start by picking a single value, in this case one of the transform coefficients, that we're going to try and produce an input signal, an input picture, that is going to maximize that value. Now, at this point in our processing pipeline, we haven't yet hit the quantizer, which comes right at the end of our encoder. And so as a result, the processing that goes from input picture to this transform value that we're interested in is an entirely linear process, meaning that we can analyze it mathematically to determine exactly what a worst case picture looks like. And in this case, we might get a test pattern that looks something like this one. Now, we can repeat this process for all of the different paths that a signal can take through our encoder, and in fact we can even generate test patterns that will maximize signal levels at intermediate processing steps in the computation of our transform. Now, once we've produced all these test patterns, we can collect them together onto a video frame and start feeding them into our codec and seeing what the signal ranges actually look like in practice. If we plot the signal levels produced by our test patterns as they're processed by our encoder, what you can immediately see is that they're producing signals very close to those of our theoretical upper bounds. And in fact, in practice, these values will be pretty much the same because, as I explained earlier, most of this processing is occurring in an entirely linear manner, meaning that our theoretical upper bounds are in fact exact values for the number of bits we need, and our test patterns, because they're computed in the exact same way by following the linear arithmetic, are hitting the exact same values. Now, unfortunately, when it comes to our decoder, things are not so simple. Now, just like for our encoders, with our decoders we can pick a value at the output of our decoder, for example, and we can trace back the values that are used to compute that all the way back to the input pixels in our original image. But unfortunately, unlike the encoder, the process that takes us from the input picture to our target pixel is not a linear one. And that's because right at the end of the encoder and before our decoder is that quantization step, which is non-linear, and therefore directly working out what a worst-case image might look like is intractable in practice. And so this is where the key contribution of our paper lies. We propose a heuristic for producing test patterns which produce extremely large signal values in a desired point in our decoder. Now, the way this works is based on the following observation. Our target pixel is the result of computations involving a whole range of input pixels. And in normal situations, all but the corresponding input pixel cancel out by the time that those values reach our target output. But as soon as our encoder introduces some quantization, those values no longer quite cancel out. And so as a result, some of the energy from those surrounding input pixels starts to leak out into our target value. Now, our heuristic attempts to maximise the amount of this leakage in order to try and make that output value as large in magnitude as possible, therefore testing out what a worst-case signal range might be for this part of our codec. Now, the degree to which these values fail to cancel out depends entirely on the amount of quantization going on, and so our heuristic aims to maximise the amount of quantization that goes on. And the way we do this is to try and make those transform values as large as possible, because large values are much harder for our entropy coder to encode efficiently in our bit stream, and so consequently it will require more quantization in order to achieve our desired bit rate. Now, fortunately, we've already worked out how to produce transform coefficients as large as possible, and that was something we did with our encoder. Now, because those transform coefficients are computed prior to quantization in our encoder, we can use our nice mathematical linear analysis technique to work out exactly what a worst-case signal is for each of those transform coefficients in turn. And as a result, we end up with a whole series of test patterns like these. Now, our objective, of course, is not to maximise these values individually. We actually want to maximise these transform coefficients simultaneously as much as we can. But for the sake of simplicity, in our heuristic, what we do is we stack up all of these different test patterns, and we place the test patterns which have the greatest influence on our target pixel at the very top of the stack, and then we squash them down into a single test pattern that looks something like this. Now, this fairly crude method isn't guaranteed to find the worst overall combination of signals, but in practice we find it does an acceptably good job. Now, just like our encoder, we can use this technique to find test patterns that maximise the signal level through every different path through our decoder. And of course, we can also use this technique to produce test patterns for intermediate stages in our decoder. Once we've got all of these test patterns, we can take them and feed them into our encoder, and then feed the resulting bit stream into our decoder and measure the signal ranges produced in there. If we plot the signal levels that were produced in our decoder by our test patterns, what you can immediately see is that we're producing signal levels much larger than any of the natural images that we measured earlier on. In addition, our signal levels are in many places very close to those predicted by the upper bound method, suggesting that we really are producing signal levels very close to the true maximum signal levels that our codec might encounter. Another feature of the results for our test patterns is that they don't track the very large peaks that appear in those theoretical upper bounds. Now, of course, our approach is a heuristic. It isn't guaranteed to produce worst-case signals, but nevertheless, it still gives us confidence that those peaks really are quite likely to be overestimates. And so, if you were to use our test patterns to estimate the number of bits you need, you might be saving as much as 3 or 4 bits in your codec, which can really start to add up in a very large codec. Now, of course, this is just a very short talk, and so for a much more thorough analysis of how our test patterns perform, take a look at our paper, which includes some much more detailed discussion of how the signal levels produced by our test patterns compare with those from a variety of sources, including the JVET test set and random noise signals. So, in summary, if you're designing or building a video codec, one of the small but important steps you need to take along the way is working out how many bits your integers need to have in order to avoid embarrassing integer overflows corrupting your pictures out in the wild. Now, existing approaches for doing this have not been ideal, and so in our paper we've introduced a new and novel heuristic that allows you to better estimate the number of bits you need in your video codec, and also to verify that your codec implementations really have used enough bits in practice. This approach is more robust than previous approaches, and it also avoids the possibility of making expensive overestimates of the number of bits you actually need. And finally, it doesn't force you to compromise on the design of your codec by introducing extra clipping and other filtering into your codec. So thank you very much for listening. If you have any questions, please do ask in the Q&A now, or you can send us an email on the address on screen. Thank you very much.